The Vision Transformer (VIT) model, adapted from natural language processing, has shown remarkable performance in vision tasks by dividing images into fixed-size patches and utilizing a learnable class token for image classification. However, it often requires substantial data and longer training times due to the computational demands of its attention mechanism. In contrast, convolutional neural networks, CNNs, possess inherent inductive bias through local filters, making them more efficient and quicker to converge with less data. This paper proposes integrating a lightweight depth-wise convolution module as a shortcut in VIT models to capture both local and global information efficiently. Two architecture variants are introduced: applying the depth-wise convolution module to multiple transformer blocks for parameter savings, and incorporating independent parallel depth-wise convolution modules with different kernels to enhance the acquisition of local information. This approach significantly boosts the performance of VIT models on image classification, object detection, and instance segmentation tasks, especially on small datasets such as CIFAR10, CIFAR100, Tiny-ImageNet, and ImageNet. The proposed method addresses the limitations of VIT models by leveraging the strengths of CNNs while maintaining the global context capture capabilities of transformers. The existing paradigm of using either convolutional neural networks, CNNs, or transformer models for image recognition tasks has limitations, particularly when dealing with small objects or abundant training data. The key challenge lies in efficiently integrating these two approaches to leverage the strengths of both. This research introduces a novel method to seamlessly integrate convolutional and transformer blocks, enabling the simultaneous learning of global and local information. The proposed approach employs depth-wise convolutions to capture local information, while transformer blocks are used to capture global information. The depth-wise convolutions serve as a shortcut, bypassing the entire transformer block, and the final combination is achieved through summation, providing a unified representation of both. This design ensures a flexible and dynamic integration of local and global features, achieving superior performance improvement with minimal additional parameters and computations. Two architectural variants are developed. One aims to reduce parameters and floating point operations, flops, by utilizing the depth-wise module to bypass multiple transformer blocks, while the other seeks to improve performance by incorporating multiple independent parallel depth-wise modules. The approach demonstrates that certain modules are dispensable when training transformer models on small datasets, and by applying the approach without these modules, both parameters and flops can be reduced, while significantly enhancing performance. This research builds upon existing vision transformer models, such as VIT, DAT, and CATE, which have introduced various improvements and applications. The hierarchical vision transformer architecture and window-based models, such as SWIN transformer, have also been proposed to reduce computational costs and improve performance. However, these models often rely on global views, which can be limited by the lack of local information. The proposed approach addresses this limitation by integrating convolutional and transformer blocks, enabling the simultaneous learning of global and local information. In the realm of vision transformers and convolutions, various models have been proposed to leverage the strengths of both architectures. Models such as CVT, botnet, local VIT, CMT, mobile former, DHVT, VITI, VTIV2, mixformer, DM-former, scope VIT, and DCTVIT integrate convolutional networks into multi-head self-attention, MHSA, or feed-forward network, FFN, layers. These models aim to merge the capabilities of transformers and convolutions for enhanced performance in vision tasks. However, some of these models may require significant computational overhead or may not be lightweight enough for efficient integration. The Vision Transformer (VIT) model introduced by Dosevitsky et al. In 2020 is a pioneering work that applies transformers to vision tasks. It involves splitting images into patches and tokenizing them, with learnable positional embeddings added to preserve spatial relations. The model consists of cascaded transformer blocks, each comprising an MHSA layer and an FF layer, utilizing residual connections and prelayer norm techniques. The class token is used for image classification, and the model outputs the result based on this token. Despite the effectiveness of ViT models, they often overlook the inductive bias inherent in images, where neighboring pixels or patches have more relations. This oversight can lead to slow convergence and require more training iterations and large datasets for optimal performance. Convolutions, on the other hand, inherently possess an inductive bias due to local filters traversing the image, capturing local details. Recognizing the complementary nature of convolutions to transformer models, especially in scenarios with small datasets, a lightweight approach using depth-wise convolutions is proposed. This approach aims to efficiently integrate transformer blocks and convolutions with minimal computational overhead, making it a versatile and straightforward module that can be easily incorporated into various vision transformer models. The proposed architecture integrates depth-wise convolutions, DW-conv, into vision transformer, ViT, models to enhance their performance, particularly when training from scratch on limited datasets. The DW-conv module bypasses the entire transformer block, allowing it to capture local details that may be missed by the transformer. This is achieved by reshaping 1D image patch tokens to 2D feature maps, applying batch normalization and JELU activation, and then performing depth-wise convolution with a 3x3 kernel. The resulting 2D feature maps are then reshaped back to 1D patch tokens and added to the output of the transformer block. The DW-conv module is utilized in all transformer blocks as a complementary component, acting as a supervisor to supervise the transformer blocks and capture details that may be missed. This approach demonstrates simplicity, effectiveness, and flexibility, unlike some hybrid models that design complex hybrid architectures. The proposed architecture is illustrated in Figure 1, and the process is mathematically represented by equations 47. The architecture variants are designed by modifying the base structure, where the depth-wise module bypasses more transformer blocks. These variants are beneficial when working with vision transformers that have deeper layers, helping to reduce the number of parameters and computational costs. However, to maintain the input and output sizes of the depth-wise module, it is recommended to limit the bypass within each stage to prevent a depth-wise module from crossing stages when multiple transformer blocks are bypassed. The use of depth-wise convolutions enables the model to capture fine details in images, a capability lacking in ViT models. The proposed approach maintains a lightweight design without significantly increasing parameters and computational demands. The DW-conv module is exploited in all transformer blocks to enhance the convergence and performance of vision transformer models. The proposed approach introduces a novel architecture variant for bypassing multiple transformer blocks, leveraging a depth-wise DW convolution module to reduce parameters and computational costs. The DW-conv module can bypass 2, 3, or 4 transformer blocks, as shown in Figure 2, and can be used to bypass an entire stage, ensuring each stage has only one corresponding DW-conv module for efficient combinations. Additionally, multiple independent parallel DW-conv modules can operate in parallel with the same or different kernels to capture local information independently, as demonstrated in Figure 3. The approach does not modify the structures of the multi-head self-attention (MHSA) and feed-forward network (FFN) modules, making it more flexible for use with most transformer models. The proposed architecture variants illustrate the flexibility of the method compared to existing hybrid architectures that combine convolutions and transformers. The transformers are greatly enhanced by the proposed DW-conv module with minimal overhead, and the structure can be easily modified to further enhance performance or save parameters and computations with different variants. A complexity analysis reveals that the proposed approach is a lightweight module that can be employed with each transformer block. Unlike some models that insert convolutional layers inside the transformer blocks, the proposed module is separable from the transformer block, making it a plug-and-play module applicable to most existing vision transformer models. The increased parameters are dependent on the depths and dimensions of the transformer models, but the increased parameters are negligible compared to the transformer backbone. For instance, the ViT Tiny model used in the experiments has 12 blocks and a dimension of 192, resulting in approximately 23,040 increased parameters, which is negligible compared to the backbone with around 5.5 million parameters. This section delves into the computational complexity of the proposed approach and its experimental evaluation on various vision transformer models. The increased calculations for the VIT-Tiny model are estimated to be approximately 4,064,256, 0.004 g, which is negligible compared to the total 1.26 g flops. This calculation ignores the number of parameters and calculations of batch norm, as they are insignificant to the model. The proposed approach is designed to be easily incorporated into various vision transformer models, introducing negligible overhead. The majority of parameters and computations still come from transformer structures, but the performance improvements are significant, especially on small datasets. Experiments are conducted on vanilla VIT, KATE, and SWIN transformer models on 3 small datasets: CIFAR10, CIFAR100, and Tiny-ImageNet. The models are also evaluated on a relatively large dataset. ImageNet 1K, and COCO is utilized for object detection and instance segmentation. The experimental settings for VIT, KATE, and SWIN transformer models are detailed, including parameter settings, dimensions, and depths. The Atom W optimizer is used with 300 epochs and 20 epochs warm-up, and the weight decay is 0.05. The batch size for the 3 small datasets is 128 with 4 NVIDIA P100 GPUs. The vanilla VIT model splits the image into small patches, which are embedded as tokens for transformer blocks. The model utilizes a positional embedding to learn the two-dimensional positional relationship between tokens. The proposed approach is applied to the VIT model without positional embeddings, and the experimental results are illustrated in Table 1. The experimental results demonstrate the effectiveness and efficiency of the proposed approach on various vision transformer models. The results show significant performance improvements, especially on small datasets. The experimental results of vision transformers, VIT, and KATE models on small datasets are presented. Table 1 shows the performance of VIT Tiny and VIT Small with and without positional embeddings, PE, on CIFAR10, CIFAR100, and Tiny-ImageNet. The results indicate that removing PE significantly deteriorates the performance, highlighting its importance in VIT models. However, when the proposed approach is applied to VIT models, there is a substantial improvement in performance, regardless of the presence of PE. For example, VIT Tiny with the proposed approach achieves an accuracy of 96.41% on CIFAR10, outperforming the vanilla VIT small model, which has almost 4x the number of parameters and flops. Ablation studies are conducted to investigate the impact of different kernel sizes and parallel DW conva modules on the performance of VIT Tiny. Table 2 shows that using a kernel size of 3 or 5, or a combination of both, achieves the best performance. The results also suggest that the proposed approach can improve the performance of VIT models even without PE. The experimental results of Chi-TXX's 12 and Chi-TXX's 24 models on small datasets are presented in Table 3. The results show that removing layer scale, talking heads attention, and PE reduces the accuracy for small datasets. However, when the proposed DW conva modules are applied to KATE models, the accuracy is significantly boosted. For example, Chi-TXX's 12 with the proposed approach achieves an accuracy of 96.43% on CIFAR10, outperforming the vanilla Chi-TXX's 12 model. The results suggest that the proposed approach can improve the performance of VIT and KATE models on small datasets, even without PE or other components such as layer scale and talking heads attention. The proposed approach achieves state-of-the-art results on small datasets, demonstrating its effectiveness and efficiency. The ablation studies provide insights into the importance of different components and the impact of different kernel sizes and parallel DW conva modules on the performance of VIT models. This section presents experimental results on the effectiveness of the proposed dynamic window convolution (DW conva) module when applied to various transformer-based architectures, including KATE and SWIN transformer. Table 4 demonstrates the impact of bypassing different blocks in Chi-TXX's 12 with DW conva modules. The results show that the accuracy drops when more blocks are supervised by DW-Conv modules, but the accuracy remains higher than the original models. This variant is suitable for deeper layers to reduce parameters and flops while maintaining relatively high accuracy. Notably, Chi-TXX's12 with DW-Conv modules achieves significantly improved accuracy on ImageNet, outperforming the original Chi-TXX's 24 model with fewer parameters and flops. The SWIN transformer architecture, consisting of 4 stages with hierarchical feature maps, is also evaluated. The shifted window-based self-attention mechanism is proposed to extend the view of tokens. Table 5 presents the experimental results on small datasets, including CIFAR10, CIFAR100, and Tiny-ImageNet. The results show that the shifted window approach has minimal effect on performance, while the SWIN Tiny model with the proposed DW-Conv module achieves significantly higher accuracy than the original model with negligible parameter overhead. Additionally, using parallel DW-Conv modules with different kernel sizes, 3 and 5, further improves accuracy in some cases, albeit with slightly increased parameters and computations. The visualization of focus areas using GRADCAM reveals that the transformer models exhibit global views of images, while overlooking some objects due to a lack of local information. In contrast, the proposed method captures both global and local information, enhancing each other and improving performance. The convergence of the proposed approach is also significantly faster than the original models, as demonstrated in Figure 5. With the proposed method reaching similar accuracy at around or less than 100 epochs, while the original models require 300 epochs. The effectiveness of the proposed method is further verified on the large dataset ImageNet 1K, with results demonstrating improved classification performance. The authors present a novel approach to enhance the performance of vision transformers, VIT, and SWIN transformers on image classification tasks. Figure 4 showcases GradCam visualizations of VIT Tiny and SWIN Tiny models, demonstrating that the proposed method captures both local details and global views, particularly for small objects. The experimental setup involves training on ImageNet 1K with a batch size of 1024 and a base learning rate of 1E3 using 8 NVIDIA V100 GPUs. The authors utilize Kate and SWIN transformer models, applying their method to each transformer block with a kernel size of 3x3 and incorporating a Depth-Wise Convolution (DW-Conv) module. For Kate, positional embeddings and talking heads attention are retained, while layer scale is eliminated. The results, presented in Table 6, demonstrate a performance boost of up to 2% on ImageNet 1K. In comparison to convolutional counterparts like ResNet, the proposed approach achieves superior performance with minimal parameter and flops overhead. This advantage is more pronounced when the transformer models have deeper layers, such as Chi-TXX's 24. Figure 5 illustrates the convergence curve of the models on Tiny-ImageNet, with the proposed method, blue curves, achieving faster convergence than the original models, red curves. Additionally, Figure 6 visualizes the convergence curve of Chi-TXX's 24 on ImageNet, highlighting the significantly faster convergence rate of the proposed approach, particularly during the early epochs, less than 100. These results underscore the effectiveness of the proposed method in improving the performance and convergence of vision transformers and SWIN transformers. This research paper presents a novel approach to enhancing the performance of transformer-based models in computer vision tasks, focusing on image classification, object detection, and instance segmentation. The proposed method introduces a new class of models called CATE, which stands for Class Attention in Image Transformers. These models leverage class attention to improve the efficiency and accuracy of transformer-based architectures. In the context of image classification, experiments were conducted on the ImageNet 1K dataset. The results in Table 6 demonstrate that Chi-TXX's 12 and Chi-TXX's 24 outperform their original counterparts, achieving higher accuracy with significantly faster convergence speed. This is evident in Figure 6, where the blue curve illustrates the faster convergence rate for Chi-TXX's 24 compared to its original model. Furthermore, the paper explores the application of the proposed approach in object detection and instance segmentation tasks using the COCO dataset. Table 7 presents the results for mask RCNN and cascade mask RCNN with and without the proposed approach. The experiments show that applying the CATE method improves the performance of both models in terms of MAP, AP50, and AP75. This indicates that the CATE models can effectively enhance transformer-based architectures in various computer vision tasks. The paper also discusses the experimental settings, including the use of AtomW optimizer, warm-up iterations, and learning rate adjustments. Additionally, it highlights the importance of utilizing 4 NVIDIA P100 GPUs for training the model with 2 samples per GPU. Overall, this research introduces a promising approach to improve transformer-based models in computer vision tasks, demonstrating enhanced accuracy and faster convergence speed. The proposed CATE models have potential applications in a wide range of tasks, including image classification, object detection, and instance segmentation. In this research, a novel approach is proposed to enhance the performance of vision transformer models by integrating Depth-Wise Convolution (DW-Conv) modules. These modules bypass the entire transformer block, enabling the capture of both global and local information with minimal overhead. The experimental results demonstrate that small transformer models equipped with this method outperform larger models with significantly more parameters and flops on small datasets for image classification, object detection, and instance segmentation when trained from scratch. The proposed DW-Conv module complements the limitation of vision transformers in capturing fine detailed information, which is crucial for object detection and instance segmentation tasks. The visualization results in Figure 7 illustrate the improvement in detecting small objects and predicting accurate boundaries using our approach with mask RCNN. The analysis indicates that our approach not only enhances the accuracy but also enables faster convergence rates for image classification, particularly on relatively small datasets. Moreover, our method can significantly enhance small-sized transformer models, even surpassing large-size original models in terms of performance on small datasets. However, the improvement might not be as pronounced when the dataset is relatively large, as abundant data can mitigate the drawbacks of transformer models. Similarly, our method may not show significant improvement for transfer learning due to pre-trained models already possessing substantial representation ability, reducing the necessity for the inductive bias introduced by our approach. In conclusion, this paper presents a straightforward yet impactful approach that utilizes DW-Conv modules to bypass transformer blocks, enabling vision transformer models to capture both global and local information with minimal overhead. Extensive experimental evaluations demonstrate that small transformer models, when equipped with our method, outperform larger models with significantly more parameters and flops on small datasets for image classification, object detection, and instance segmentation when trained from scratch. The authors introduce several architecture variants tailored to different models and objectives, anticipating further research on vision transformers, particularly in the context of small datasets. They acknowledge the support of the Natural Sciences and Engineering Research Council of Canada, NSERC, under grant numbers 15,148,183 and 15,148,933. The authors cite various papers that have contributed to the development of vision transformers, including Vaswani et al.'s work on attention mechanisms, Dosevitsky et al.'s application of transformers to image recognition, and Howard et al.'s mobile nets for efficient convolutional neural networks. They also reference Patel et al.'s work on aggregating global features into local vision transformers, Chen et al.'s accumulation of trivial attention in vision transformers on small datasets, and Zhu et al.'s biformer with bilevel routing attention. Furthermore, the authors cite papers that have applied vision transformers to various tasks, such as point cloud completion, Wang et al., audio-visual crowd counting, Sajid et al., and image transformers with attention-based distillation, Tuvran et al. They also reference works on training data-efficient image transformers, Tuvran et al., going deeper with image transformers, Tuvran et al., and pyramid vision transformers for dense prediction, Wang et al. Additionally, the authors cite papers that have rethought spatial dimensions of vision transformers, Heo et al., improved vision transformers on small datasets through token pooling and attention sharing, Chen et al. And hierarchical vision transformers using shifted windows, Liu et al. The pages present a comprehensive overview of recent advancements in vision transformers, bridging the gap between convolutional neural networks, CNNs, and transformers. Several studies have been conducted to explore different architectures and techniques that leverage the strengths of both CNNs and transformers. One such approach is the MSG transformer, which exchanges local spatial information by manipulating messenger tokens. 16. This model aims to enhance the spatial attention mechanism in vision transformers. Another approach is the twins architecture, which revisits the design of spatial attention in vision transformers. 17. It introduces a new spatial attention mechanism that adapts to different input sizes and improves performance on various image recognition benchmarks. The shuffle transformer, 18, rethinks spatial shuffle operations for vision transformers, while the CVT model introduces convolutions to vision transformers. 19. Bottleneck transformers are also proposed as an alternative to traditional transformer architectures. 20. They reduce the number of parameters and computations required, making them more efficient for visual recognition tasks. In addition to these architectural innovations, researchers have applied vision transformers to various applications such as wetland mapping, 31, salient object detection in optical remote sensing imagery, 32, and scene understanding from aerial imagery, 33. For instance, the wet map former model combines deep CNNs and vision transformers for complex wetland mapping tasks, 31. Similarly, the hybrid feature-aligned network, HFA-net, utilizes both CNNs and transformers for salient object detection in optical remote sensing images, 32. Moreover, vision transformers have been used in tasks like referring image segmentation, where the local global coordination with transformers, LGCT, model demonstrates improved performance by leveraging the strengths of both CNNs and transformers. 34. Other models, such as DM-Former, 28, ScopeVit, 29, and DCTVIT, 30, further explore different techniques to enhance the capabilities of vision transformers. These advancements collectively aim to improve the efficiency, effectiveness, and adaptability of vision transformers in various image recognition and segmentation tasks. They demonstrate the potential of integrating CNNs and transformers to leverage their respective strengths and address their limitations. This section reviews various techniques and architectures in deep learning, highlighting their relevance to the development of vision transformers. Layer normalization, introduced by Ba et al. 35, is a widely used technique for stabilizing training. Gaussian error linear units, GELUS, proposed by Hendricks et al. 36, or a type of activation function that has been shown to improve model performance. Batch normalization, introduced by IF et al. 37, is a technique for normalizing the input to each layer, which has been widely adopted in deep learning. The Tiny-ImageNet dataset, introduced by Krzyzewski et al. 38, is a popular benchmark for evaluating the performance of deep learning models. The ImageNet Large-Scale Visual Recognition Challenge, ILSVRC, introduced by Rusikovsky et al. 40, is a widely recognized benchmark for evaluating the performance of image classification models. The Microsoft COCO dataset, introduced by Lin et al. 41, is a large-scale dataset for object detection and segmentation. The atom optimization algorithm, introduced by Kingma et al. 43, is a widely used optimization algorithm in deep learning. Auto-augment, introduced by Kubik et al. 44, is a technique for learning augmentation policies from data, which has been shown to improve model performance. Random erasing, introduced by Zhang et al. 45, is a data augmentation technique that randomly erases a portion of the input image. The mix-up algorithm, introduced by Zhang et al. 46, is a technique for generating new training data by mixing two images. Cut mix, introduced by Yun et al. 47, is a regularization strategy that trains strong classifiers with localizable features. Conditional positional encodings, introduced by Chu et al. 48, are a technique for incorporating positional information into vision transformers. The MIDI-Dieter architecture, introduced by Ma et al. 49, is an object detection model based on transformers with mitigatory self-attention convergence. GradCam, introduced by Selvaraju et al. 51, is a technique for visualizing the features learned by deep networks. The ResNet architecture, introduced by He et al. 52, is a widely used architecture for image classification. The Squeeze and Excitation Network, SENET, introduced by Hu et al. 53, is a technique for improving the performance of deep networks by modeling the relationships between channels. The VisFormer architecture, introduced by Chen et al. 54, is a vision-friendly transformer that incorporates a new type of attention mechanism. The referenced papers by He et al. 57 and Kai et al. 58 are discussed in the context of object detection, a fundamental task in computer vision. He et al.'s Mask RCNN 57 is a seminal work that extends the faster RCNN architecture by adding a segmentation branch, enabling the model to predict pixel masks for object instances. This innovation allows for more accurate object detection and segmentation, particularly for objects with complex boundaries. Kai et al.'s Cascade RCNN 58 builds upon the faster RCNN architecture, proposing a cascaded detection framework that iteratively refines object proposals and classification scores. This approach enables the model to focus on high-quality object detection, achieving state-of-the-art performance on various benchmark datasets. Both papers employ a region-based convolutional neural network, RCNN, architecture, which generates region proposals and subsequently classifies each proposal using a neural network. He et al.'s Mask RCNN augments this architecture with a segmentation branch, comprising a fully convolutional network, FCN, that predicts pixel masks for object instances. Kai et al.'s Cascade RCNN, on the other hand, introduces a cascaded detection framework that refines object proposals and classification scores through multiple stages. The mathematical formulation of both approaches relies on the intersection over union (IOU) metric, which measures the overlap between predicted and ground truth bounding boxes. He et al.'s Mask RCNN uses the IOU metric to train the segmentation branch, while Kai et al.'s Cascade RCNN employs a cascade of IOU thresholds to refine object proposals and classification scores. The experimental results presented in both papers demonstrate the effectiveness of these approaches in object detection and segmentation tasks. He et al.'s Mask RCNN achieves state-of-the-art performance on various benchmark datasets, including the COCO dataset. Kai et al.'s Cascade RCNN also achieves competitive results on the COCO dataset, outperforming other state-of-the-art object detection models. The flow of ideas between the two papers is evident, as both approaches build upon the RCNN architecture and employ similar mathematical formulations. However, each paper introduces novel ideas and methodologies that contribute to the advancement of object detection and segmentation research.